Good morning, students. Now we will be continue the last class. In the last class, we discussed the kinetic energy gained by the charged particle when it is left in a uniform electric field. The same case. Now we will be continue further one. If a charged particle is projected in a uniform electric field, then what is the deviation produced in it? That we will be discussing. So the deviation produced in a charged particle, the deviation produced in a charged particle let us take a uniform electric field like this. So how to produce uniform electric field? We discussed two metallic plates. One is positively charged, another one is negatively charged is there. Then electric field will be from positive side plate to the negative plate. What will be their uniform electric field will be produces. So this is the way you can able to produce uniform electric field. In this uniform electric field, if you projected a charged particle, so I am projecting a negatively charged particle. So in this a negatively charged particle is projected here. This is a negatively charged particle. Then obviously this negatively charged particle with an initial velocity v0. The velocity initially we are projecting v0. Then if you taken the coordinates, this is along x-axis, y-axis. So initially we are provided the velocity along x-axis only, but along y-axis the velocity is 0. So we can say initial velocity is there, that is initial conditions I am taking. Here initial velocity ux is equals to v0, but initially there is no particular velocity, so uy is equals to 0. So when it is entered into the magnetic field, what will happen? It will experience force. That force will be what? Along the direction opposite to the electric field. Why? Because the positive charge means that is that experiences in the direction of field. Negative charge means it is experienced in the direction opposite to the field. Actually, no force is experienced by it in the sense it will be travels along the straight line path. So if it is no force is experienced by this particle, you may understand it is no deviation, it will be travels in a straight line path. But here the force is acting upwards. That force F equal to, we know F, force is acting upwards. So this charged particle experience force F equal to EQ. So along which direction means upwards, that is along y-axis side. So then how much of acceleration is produced in it is acceleration is ay, we can write. Why? Because along upwards y-axis side, ay, that is equal to F by m, so EQ by m. So it will be accelerate upwards, but along x-axis there is no such kind of acceleration. Along x-axis acceleration 0, but along y-axis acceleration is EQ by m. So I am writing that along x-axis acceleration is 0, along y-axis acceleration is EQ by m. So now initially this is the thing will be happens. Initial velocity v0, that is along x-axis. We are not providing any velocity initially along y-axis. Later, after going to entered into the magnetic field, after traveling, it is experiences force upwards. That force, you know, it is a charged particle. When it is placed in an electric field, the force is EQ. Then how much of acceleration produces along y-axis is that is ay equal to F by m. There is no force is EQ, that is EQ by m. But along x-axis there is no force. No force, so Ax is equals to 0. And also compared to the acceleration produced by the electric field, the gravitational acceleration is very much negligible. That's why here I am not considering the gravitational acceleration. So neglecting gravitational acceleration. So gravitational acceleration is negligible. Now the case is, it is force is experiencing upwards, no? So this will be deviated. Actually it has to travel like this, but it is deviates like this. Slowly deviates and it is goes like this. So here if you place a screen, it will hits this screen after coming out. So this is what the vertical distance traveled by it, and this is the horizontal distance traveled by it. So this vertical distance is nothing but we can call it as a deviation. So from the actual path, this is the actual path, how much it is traveled vertically upwards, that is what we can say deviation here. Now this y we need to be determined, as well as x we can able to determine it. So this is we can follow like this. Initially, see here, initially only horizontal velocity, vertical velocity is 0. So from equation Sx is equals to uxt plus half ax t square. From the equation of motion, Sx is equals to uxt plus half ax t square. Here you know, along x-axis velocity is v0, but along x-axis acceleration is not there, because acceleration is acting along y direction. So initial acceleration is along x-axis, acceleration is 0. That if you write, and here Sx is if you taken as a x, then you will get x is equals to v0 t. This is equation 1. Next, from equation you can write that from equation Sy is equals to uyt plus half ay t square. So you have the expression that uy, initial vertical velocity is 0, so uy is 0, and along y-axis acceleration is we have eq by m, under time t. So that is time is you write as it is, so time t. Then sy you write as a y. Then if you substitute that y, you will get 0, because u is 0, half eq by m into t square. So this is the vertical distance traveled by the particle. And this path you can also say as a parabola. So how can you say this as a parabola? In the sense you observe that, so this is the deviation you observe here. So how much of vertical distance traveled from the mean position, that is deviation, that is you can write half eq by m into t square. And this path also we can write as a parabola. That is how can we write, means from t we can write x by v0, from 1 t equal to x by v0. So that if you substitute here, if you substitute that one here, so from 1 and 2, y equal to half eq by m, t place will write x by v0 whole square. Then we can write y equal to eq by 2m v0 square into x square. Then you observe uniform electric field E remains constant, and as well as the charge is remains invariant. Charge invariant in the sense we know when a charge is in motion, it is magnitude is never changes, and m mass will be remains constant v. So v naught is the initial velocity. So all these terms are constant. Then y proportional to y equal to some kx square. So this equation represents the parabola. So you can say the path of the charged particle in the what uniform electric field is parabola, we can say. And so this path indicates the path of the charged particle is a parabola. So that is we can write. Next we will go for the another case that if a charged particle is projected by making an angle theta with horizontal in a uniform electric field, what is its velocity or what is the position after time t seconds that we will be discussing. So if a charged particle is projected by making an angle theta in a uniform electric field, if a charged particle is projected by making an angle theta with horizontal in a uniform electric field. So if a charged particle is projected by making an angle theta with a horizontal in a uniform electric field, let us see. You take this is a x and y axis. Now we have a uniform electric field upwards. Let us take the uniform electric field is upwards. This is the uniform electric field. So in this uniform electric field, we are projecting a charged particle by making an angle theta. So which kind of charged particle we are projecting? In the sense, negatively charged particle we are projecting. So a negative minus q charge is projected with initial velocity u, making an angle theta with horizontal. So now if a charged particle is projected like this, you observe this is a charged particle q is projected like this with initial velocity u. When it is projected upwards, the charged particle will experience force downwards. Why? Because electric field is upwards, no? Negatively charged particle will experience force in the downward direction. Negatively charged particle experience force in the downward direction means here acceleration A, we have force F is equals to EQ, then A equal to EQ by M, along which direction? Downwards. So it is along downwards. So what is the acceleration here is A equal to EQ by M, which is acting downwards. And G is neglected. Acceleration due to gravity we are not considering. G neglected. Now you observe when it is going upwards, so what will happen? This acceleration will tends to be reduces its velocity. And again what happens? Then its velocity keep on decreases and reaches to maximum height. Again when it is coming back, velocities keep on increases, just like a projectile motion how you seen. Same way But here in place of projectile motion you taken that only gravitational acceleration, but here we are taking that in place of gravitational acceleration eq by m. That is only the difference, remaining everything is same. Now if it is projected with an angle theta, then it will be ux is u cos theta, and it is uy is u sin theta. Ux u cos theta, uy is u sin theta. Then if you resolve this like this, we will get now horizontal distance traveled by it, vertical distance traveled by it, we can discuss it. So first we will discuss what is the velocity after the t seconds. You know, if acceleration along y direction, u cos theta will not be gets affected. Only here u sin theta will be affected. That is because of acceleration is vertically acting. Horizontally there is no acceleration. Acceleration is not there. Velocity remains constant. So u cos theta will be remains constant throughout the motion. But u sin theta will be reduces, and finally it will becomes 0 at a particular point. And again what happens here, it will be increases in the reverse direction, and again it is increases in the reverse direction. This is the already you studied in the first year of projectile motion. Now projectile motion, that is under gravitational acceleration. Now this is the projectile motion under what? Electric acceleration, electric force acceleration here. Now velocity after time t seconds, velocity of the charged particle after time t seconds. So velocity of the charged particle after time t seconds, in the sense we can write as a v x equal to uxt, from the formula vx is equals to ux plus axt. Here you know ux in the sense v u cos theta, but ax along x-axis there is no acceleration. Therefore velocity after time t seconds is only u cos theta. Velocity remains the same. Next, vy equal to uy plus ayt. So vy equal to uy in the sense u sin theta. Ay is downwards in the sense body is projected upwards, but acceleration downwards, no, it is retards. It is a retardation because it is opposes the motion. So that's why whenever the acceleration is opposing the motion, that is, we will say retardation. That retardation means you have to provide the negative sign. Then we can write ae is equals to eq by m into t. So this is the velocity. So initial velocity, and this is the along x-axis, final velocity along x-axis, and final velocity along y-axis. And vector form can usually write, therefore v equal to vx I cap plus vy j cap. Here vx in the sense u cos theta, vy in the sense u sin theta minus eq by m into t. So this is the velocity vector after time t seconds. So velocity vector after time t seconds, velocity vector after time t seconds. Next, positions, you have to discuss it. Position in the sense what is the position, because initially it is at origin. Initially it was at origin. Now after time t seconds, where it is goes. Suppose here it is a position we took here. So it has x direction, y direction. So along y direction, what is the position? What is the along x direction? What is the position? So that is, you want it in the sense along x direction how much it will travel after time t seconds. Along y direction how much it will travel after t seconds. We need to be find it out. So position after t seconds, position after t seconds. Same procedure we will following, that is Sx is equals to, so position in the sense we have the uxt plus half ax t square. So initially horizontal velocity ux is u cos theta, but is there any acceleration along x-axis? So it's no. So acceleration along x-axis is 0. Therefore Sx means you can write as a x, so we can write the formula x is equals to u cos theta into t. This is a horizontal distance traveled by it. Next, Sy is equals to uyt plus half ay t square. Along vertical direction, the velocity is uy equal to, you can write as a u sin theta, and you know acceleration is there along downwards, so it is opposes the motion, so you can write ay in the sense of minus eq by f, that is downwards. Then if you substitute sy in the sense, you can take it as a y, so y equal to u sin theta into t minus half eq by m into t square. So this is the position. Based on this position vector after time t seconds is, you can write as a position vector after time t seconds, that is r bar equal to xi cap plus y j cap, that is x means you know u cos theta into t and y means u sin theta into t minus half eq by m into t square. This is the what when a charged particle is projected by making an angle theta with horizontal in a uniform electric field, velocity after time t seconds and as well as the position after time t seconds. This is the case you have to be discussing, because they may ask you electric field intensity and the charged particle mass, everything they will provide us, and what is its position after time t seconds, in the sense you can follow this procedure and you can calculate that. Next we can go for the time period of the oscillation of a charged particle in a electric field. Let us suppose the time period of oscillation of a charged particle in uniform electric field. Let us take a charged particle. We will take it. Generally, if a charged body is there, this is the rigid support. Here, body, pendulum, whose length is L and whose mass is M. And what is the time period of it? Already we discussed, that is t equal to 2 pi into root over L by G. So when it is oscillating in a gravitational field. So when it is oscillating in a gravitational field, the time period expression is t equal to 2 pi into root over L by G. So now this case is belongs to charged particle is in a uniform electric field. So if it is in the absence of electric field, it is only having gravitational field. Gravitational field means their net acceleration here you taken the denominator as g. Okay, it is in the absence of electric field. So in the absence of electric field, we have the time period expression is t equal to 2 pi into root over L by G we have. Now here A net acceleration is g only, that's why we took T equal to 2 pi into root over L by G. So now we'll discuss the cases of if electric field is present. First case, if this is the odd pendulum and this is the charged particle. So if you whatever charge you can take it, that is no issue here. If you take a positive charge plus Q and it has some mass M. Now if the electric field is, you are acting upward direction. So electric field is upward direction, it is there. Now it is in the presence of what? Uniform electric field upwards. Then you may observe because of this electric field it will experience force F equal to EQ in the upward direction, and because of mass it experience weight mg downward direction. Then the net force in the downward direction is we can write F net in the downward direction, F net equal to mg minus EQ. The net acceleration downwards is A net equal to, so we can write mg minus EQ by m. Then A net equal to, you can write g minus EQ by m. So this is the net acceleration downwards. Then earlier we seen that is in the absence of electric field we have the time period means what 2 pi into root L by G. Their net acceleration downwards is what? Only G is there. Then you wrote here denominator G. But now the net acceleration downwards is G minus EQ by M. So what is the time period expression? Now it is going to be changed. Here is the time period T dash is now 2 pi into root over L by G plus, now we will write G minus EQ by M. So G plus, now it is, we can write as a G minus EQ by M. This is the new time period when the electric field is upwards when you are taken the positive charge. The same way, if you take the another case that if the pendulum is there like this and the charged body is suspended and it is oscillating also, don't think it is in rest, it is oscillating also. Now if the electric field is downwards, then electric field is downwards in the sense EQ and as well as gravitational force. Now you observe electric field is downwards, so charge plus Q and mass M. Now because of electric field it is experience force, that is EQ downwards as well as weight mg downwards. So what is the net force downwards here is, here net force down in the sense mg plus EQ. So mg plus EQ in the sense net acceleration, you can write F net by mass. So mg plus EQ by m, that is the net acceleration. Here we can write as a g plus EQ by m. So earlier we have the previous case, one is upwards, another one is downward. Net downward force is mg minus EQ, but electric field is downwards in the sense the force exerted on this charge is downwards only, that is EQ, and you know always the gravitational force is acting downwards. Then the net acceleration is g plus EQ by m. So the new time period now we can expect here, so 2 pi into root over L by, what is the g effective acceleration downwards is g plus EQ by m. So this is the thing you can understand when electric field upwards and electric field is downwards. Next, if electric field is so upwards in the sense, if a charged body is there, that is g minus EQ by m, and downwards is there, that is g plus EQ by m. Then if it is horizontally, if it is there, horizontally it is there, suppose third case we are taking like this. If the pendulum is there, now electric field is in this direction. So it is not upwards or downwards. Now it is in the horizontal direction. Now you observe the charger body pendulum is here, is plus q, whose mass is m. So electric field is there upwards, means the electric field is there upwards in the sense the force is experienced upwards. Electric field down is there, the force experienced downwards. But electric field towards in the right hand side, then this force will experience in the right side. So if this is will be gets displaced here, what will happen? This bob will be experience a electric force F equal to EQ, because it is a positive charge, so in the direction of field. Here the net downward force is F equal to mg. So here two forces are there, then the resultant force is nothing but this is the F net. So net force here is we can take it as a two forces are perpendicular to each other. Then F net force here we can write root over, because two vectors are perpendicular to each other. If then it is under root of F1 square plus F2 square. In the same way here, mg square plus what EQ square. Therefore we wanted net acceleration, so A net in the sense F net force by mass. Then if you taken that, you will get g square plus EQ by m whole square. So this is the net acceleration down. So net acceleration experienced by the charged particle. Now the new time period t dash equal to 2 pi into root over L by, now what is the net acceleration here? G square plus EQ by m whole square under root. So this is the new time period when electric field is along right side horizontally. Now fourth, here one more case. If the pendulum is there like this, it is a plus q charge. Now here one charge you located exactly at the point of suspension. So a charge is located at the point of suspension. What is the new time period? Here a charge is located at point of suspension, new time period. See, whenever charge is located at the point of suspension, if you take the bob at this position, plus q, here q naught, this q naught will be exit the field radially. So the electric field of this q naught, the electric field produced by this q naught is along the direction of the pendulum. Then when it is along this direction, we cannot be resolve this. Suppose if it is make some angle with vertical, means it is see here in this case it is along horizontal, means we can resolve this component. But if this is along this direction, in the sense we cannot be resolve this into component. So here the component of electrostatic force not acting as a restoring force. The component of it is not acting as a restoring force. So the component is not acting as a restoring force in the sense what happens here, we cannot be, means only even if it is charge is present, it will be, even charge is present means this force does not influence this charge. If this force does not influence in the sense, if in the absence of electric field, with what time period it is oscillating, now also be oscillates with the same period, that is original time period, that is t equal to 2 pi into root over L by G. So we can say that the component of electric the component of electric force, no component, you can say, no component of electric force acts as a restoring force. No component of electric force acts as restoring force. So it is not affected. Therefore, no time period will be then t dash equal to, we can say, 2 pi into root over L by G only. If it is other direction is there, along this tension is there. Suppose if you take this position, if this position, here also electric field is EQ like this only. If you take this position, electric field EQ like this only. Always electric field tends to be act along the direction of this pendulum. Then we cannot be resolve such case, because one fixed direction is there. We can say we can resolve into angle, but he is always acting in the direction of the pendulum, in the sense we won't be resolve it. Then if we won't be resolve it means there is no such kind of restoring force acting to bring it to the what mean position. So time period is not affected, only it is influenced by gravitational acceleration only. Okay, so it is not influenced with the electric force. That's why the time period will be remains same. So when this is remains same, in the sense at the point of suspension, if any charge is located. So this is the thing you can understand. Next, here we have several other cases also be there, like if charges are located, two charges are located, one more important model, and it is a repeated problem which is given in the what examination, that is we will be discussing few numericals related to this board as well as the objectives. So an example I am telling you here, two charges are there. Those two charges are located at the two corners of an equilateral triangle. Then what is the force experienced by what is the net electric field intensity at the third corner? If two equal charges are placed at the two corners of an equilateral triangle, then electric field intensity at third corner. So you can observe here, if charges are located, this is an equilateral triangle whose side length is L. Here charge A, B, C. Here charge Q, here Q. So what our intention means, two charges we located at the two corners. Because of these two charges here, what is the electric field intensity? Let us use same cases we discussed in the force also. So similar cases here. Due to these two charges, what is the direction of electric field intensity? First you have to be discuss it, and later we have to find the resultant of those two electric field intensities. Due to the charge at A, here electric field intensity is which is away from it because of positive charge, that is E1 you take, and because of this charge electric field intensity is away from it, that is E2 you take it. And you know here this is angle equilateral triangle they mentioned, so equilateral triangle in the sense 60 degrees, so vertically opposite angle this is also be 60 degrees. Then E1, what about E1 here? E1 is equals to, 1 upon, what is the electric field intensity due to point charge is 1 upon 4 pi epsilon into Q by R square, from where you want to find the electric field intensity. Here charge is Q, and due to this charge here you want it, the distance is L, so L square, which is away from it along AC. Similarly E2 in the sense that is 1 upon 4 pi epsilon naught, then it is away from it, that is you can write Q by L square, and along BC. So these two, if you observe, magnitude of E1, magnitude of E2, both are same, and angle is 60 degrees. Then resultant we can find, resultant electric field intensity is under root of E square, means E1 square plus E2 square plus 2 E1 E2 cos 60 degrees, resultant electric field by using the parallelogram law of vectors. Then if you substitute, all are same, no, here magnitude these two are same. Then if you taken that E square plus 2 E1 E2 is E only, so E square cos 60 is 1 by 2. Then it is root 3 times the E you will get. So electric field intensity here root 3 times the 1 upon 4 pi epsilon naught Q by L square. So like this you can able to find it out electric field intensity at this place. Suppose if it is one of the charge is negative, the one of the charge is negative, how can you say here is, if charges plus Q and minus Q are placed, plus Q and minus Q are placed at the two corners of an equilateral triangle, then what is the force, what is the electric field intensity at the third corner? Then electric field intensity at the third corner. Earlier we taken that both are positive charges. The electric field intensity is root 3 times the 1 upon 4 pi epsilon naught Q by L square. Now here these are opposite charges. Now if you take the same case, let us take here A plus Q, at B minus Q, C. Here the electric field intensity due to these two charges is, because of positive charge the electric field intensity is away from it. So away from it in the sense equilateral triangle, all the side lengths are same, away from it, that is E1. But due to negative charge, this negative charge, the electric field intensity is not away, it is towards it. So towards it means this is E2 will be towards it. Magnitude wise no change, but only the thing is direction only be affected here. So already you know it is angle 60 degrees, then angle between this E1 and E2 is now it is 120 degrees. So magnitudes are same only, because here distance same, charge is also be same, only nature changes means direction changes. Then I am directly we can write E1 equal to 1 upon 4 pi epsilon naught Q by L square along AC. Now E2 means 1 upon 4 pi epsilon naught, but towards it now Q by L square and along now it is reversed along the CB. Therefore now 120 degrees, and again the magnitudes are also be equal. Now angle only be different, so resultant electric field intensity, so you can write under root of E1 square plus E2 square plus 2 E1 E2 cos 120. These two magnitudes are equal, so we can write root over E square plus E square plus 2 E square cos 120 minus 1 by 2. 2 gets cancelled, plus U square minus U square cancelled, then resultant electric field intensity is E, that is 1 upon 4 pi epsilon naught Q by L square. So this is the electric field intensity when one is positive and another one is negative. Suppose here we taken same magnitude of charges, one positive and another one negative, and same, both are same positive, so it is quite easy. But if the charges are different, means one is Q1, another one is Q2, so we have to be proceed as usual the procedure only, that is how much of electric field intensity is there. So that is we have to be find it out by using the parallelogram law vectors, even the direction also. So we will be discuss such one kind of example here. So now we can discuss that if two different charges are located at two corners of an equilateral triangle, then electric field intensity at the third corner. Now I am going to take that here one is Q1, another one is Q2. I am going to take like this Q1 and Q2. Different charges I am taking. What is the electric field intensity at this point? Let us you take now as A, B, C, and I am taking the equilateral triangle same length. Then electric field intensity due to this charge Q1 at this point C is it is away from it. So this is E1. That E1 is we know expression 1 upon 4 pi epsilon naught into what, Q1 by L square. So along AC. Similarly, this is if you taken this has a negative charge, two different charges, one is plus Q1, another one is plus Q2 if you taken. Now this is electric field intensity is away from it, that is E2. Now E2 equal to 1 upon 4 pi epsilon naught Q1 Q2 here, Q2 by L square along BC. Here E1 E2 not equal, E1 not equal to E2, then you have to be, follow the procedure as usual. These two angle is 60 degrees only, then you have to be follow the as usual procedure, that is E resultant equal to root over E1 square plus E2 square plus 2 E1 E2 cos 60 1 by 2, then it will be ER equal to root over E1 square plus E2 square plus E1 E2. So individually here charges they will provide it in numericals, so those you have to be calculated, then you have to be substitute in the expression, then you will get the resultant electric field intensity. Later you have to be find the direction. So later find the direction in the sense how much it is making angle, how much it is making angle theta with vertical or with E1 or E2. Suppose if you want to find the angle made with E1, this is alpha. That alpha, how can you write here is here angle tan alpha equal to, that is we can write as a E2 sin theta by E1 plus E2 cos theta. Like that we will be use this formula, then we can able to, what is alpha here? Here alpha is the angle made by resultant with E1. So this is the resultant with E1. So you have to be calculate these two. Substitution, if you done here, if you do here, you will get the resultant. Magnitude you will get here. So direction if you want it. Direction if you want it means angle you have to measure it. So that angle tan alpha equal to E2 sin theta by parallelogram of vectors. Once you refer, then you know this formula it will come. So in this alpha is the angle, this alpha equal to E2 sin theta by E1 plus E2 cos theta. Here theta in the sense 60 degrees. We know well it is 60 degrees here theta. So theta equal to 60 degrees. Then if you substitute it, you will get the alpha, that is angle made by this resultant with E1. So in this way you have to be solve it. So we can do one example in the next session.